Welcome to you all this new YouTube channel of Alien Lecture. My name is Rukshana Tapato. Let's move to the lesson. Today lesson is a red black tree. First of all, do you know binary tree? I think you know binary tree definitely. Let's check whether if you memorizing your few principles of the binary tree. We know the every nodes have minimum the maximum two subtrees, two child subtrees, and the left subtree is lesser than the parent node, and the right subtree is greater than the parent nodes. Okay, now move to the red black page. A red black tree is a kind of the self-balancing binary searching tree where each node has an extra bit, and that bit is of inspiration as the colors red or black. These colors are used to ensure that the trees remaining balancing during the inspiration and deletions. Although the balance of the tree is not preferred, is good enough to reduce the searching time and maintain around big O login time, where n is the total number of elements in the tree. Okay, let's move to the next page. We can say average case of the searching tree is big O log n, but the worst time is big O n. Somehow we can feel in this scenario is in big N number of elements. We'll see what is the meaning of this. If we assume it is a binary tree, this kind of, if we check our elements is in here, come to the root node and check whether our value is lesser or greater than this root's value. If it is lesser, we go to the this side and check whether against this our value is lesser or greater. If it is a greater, we go to this way. This kind of sequence is check whether our value is in here or not. We can idea get. So we can understand in here the height of the edge is the time complexity of the searching searching. So that is why the average case is a log n is the time complexity. Now we'll check whether the what is the big O n. If we assume this kind of binary tree, we can understand in here. If we check whether our value is in here, come to here, check whether it is a greater or lesser. If it is a greater, it's no element. We can definitely tell our value is not in this tree. If it's a lesser, we can move to the here and check against and against and against. So we can check. It is a similar. We can see it is a similar to the linear. It's mean if we check the way that in the element is in the list is similar. So it's got in time of we go in. So it is a wasting our time. So that is the meaning of this scenario. This sentence means. Okay, let's move to the next. The AVI tree are more balancing compared to the red black trees. Uh, but there are cases more rotational during the inspirations and deletions. So if your applications involve the frequency of insertions and deletions, then red black trees should be preferred, and if the insertion and deletions are less frequent and search is more frequent operations, then AVL tree should be the preferred over red black tree. Okay, in this tree versus the inverted in 1972 by the Rudolf Beer. Okay, let's move to the some few operations of the red black tree. They have searching, search, insert, and deletions. We can understand the time complexity is big O log n. We move to the rule that every red black tree follows. It is a self-balancing BST. Every node has a color either red or black. The root of the tree is always black. Uh, how do we memorizing these three principles? Okay, we get some example. We know all the families have grandparents. They are more cool and more sensitive than the other people. I mean, school. For they are so we can they are similar to the black color because other peoples are not cool. They are always rushing and so they are always angry. So we can tell that they are similar to the red color. So we can understand. For we can implement in this example, the root node is always black color. Okay, we go to the next law. There are no two adjacent red nodes, and the next is every path from the node to any of its descendants null nodes has the same number of black nodes. Okay, we check whether if you understand this law in by using the example. Okay, let's move to the example. Our first example is this. Okay, there our the law have the null nodes. Okay, first of all, we what is the null nodes? Null node is the leaf. It is a add of the leaf node. So we put in here. Yes. The leaf null node's color is black. Okay. Now we'll check whether it is a binary tree. It is a they have every node they have two child and the value is the root value is the value is lesser and this value is greater. No other value is following that scenarios. Okay, we can tell this is a BST and it is every node has a color either red or black. You can see that every node has black color. So the root node is always black. So these three conditions are proving. So the other condition that there are no two adjacent red colors nodes. So we can understand they have no any red color nodes. So we can't check whether this law is proven. The other we will check the other law. It's mean in they have few paths to the come to the leaf node. This is the first path and this is the second path and this is the third path and this is the fourth path. This is the fifth path and this is the sixth path. In first path we can say they have one. We didn't get the root node to the following how much have the black nodes. So it is because it is a definitely the black. That's why. Okay, in this path we have 1, 2, and 3. This path 1, 2, 3. This path 1, 2, and 3. Other path 1, 2, and 3. In this path 1, 2. In this path 1, 2. So we can see these the same number of black nodes are not in here. So we can tell this is not a red black tree. So okay, now we move to the next example. We can in this example we can see that the root node is red. So we can remove this. This is not this is not a red black tree. So we can't we so we don't check the other condition. So we move to the next example now. In here, this example, we can see the if we assume, first of all, this node is black, sorry, red. Okay, we can see that we can't put two adjacent nodes in same color. So it is definitely it can't be red. So it definitely black color. I want to implement this law. So how do we use it? Okay, now we check whether the other condition. If we check, this is a binary tree. No, it is not a binary tree, because why I say that way? Because this 11 is greater than. So how do we put in here? It's always in the right side. So we can say it is not a binary tree. Okay, we now move to the next example. In here, we can say, we can see this is a binary tree because the value are always implementing the binary tree, same as a binary tree. Null, we mark as a null points now. Okay, you can see the two red nodes are adjacently now. So we know they have no two adjacency red nodes in here. So we can tell this can't be red. So this it definitely be black. Okay. Now we'll check whether it is a red black tree or not. In this part, we can see 1, 2, 1, 2, 1, 2, 1, 2, and this part 1, 2, and 1, 2. So we can tell this is a definitely red black tree. Okay, we move to the quick move to the next example. Okay, this is a main example because okay, let's move. In here we mark as a null point now. Click. Okay. Okay. The lowest, the least leaf node had 1 and 2. Two black nodes. In this path, 1, 2. Two black nodes. But the special thing is in here, it has 1, 2, 3, 4. 4 node is using in here. Okay, but they have only 2 black nodes. So we can tell in here the special scenario. The longest path through his leaf node cannot be more than twice of the shortest path to the leaf node. It is a special things in implementing the red black tree. Okay, let's move to the end of our lecture now. The applications. Applications of the self-balancing BST library functions like map and set in the C++ using the red black trees. It is used to implement a CPU scheduling link Linux. Besides, they are using the k-meaning clustering algorithm for reducing the time complexity. The next is moreover, MySQL also used to red black tree for indexing on table. Okay, so we today see the what are the red black tree, what are the applications, how do we identify the red black trees, these kind of things. So the today lecture is finished, and thank you all. Be with us, and let's me meet us with next video. Thank you.